Hello everyone, so welcome back to our latest lecture session. So I believe in the last sessions we have been talking about or discussing titrations and buffers. So buffer is one you would look at, let's say when you want to resist the change in pH when an acid or base is added, and we looked at the relevant examples I believe for what is it now, monoprotic acid, which I think we looked at with respect to acetic acid, and then we looked at diprotic acid, which in that case we considered carbonate system. So, or the carbonic acid and the relevant acid base species. So again, we are now going to come back to designing buffers. I believe we briefly discussed this earlier, but we are going to see or briefly summarize what we are up to, right. So design of buffers. So when you are trying to design a buffer, what does this mean? You want to choose the relevant acid base system or the species, right? And you also want to know how much acid or the base that you need to put into your system, right? So what are we trying to look at? Which particular acid base to add, right? And also how much of the acid base do you want to add? So how do you come up with this now, right? So for this obviously you need to be able to look at what it is that you need, as in what pH change are you comfortable with. So only then can you be able to come up with the relevant buffer intensity, right. So we know that the buffer intensity, what was that equal to? -1 by derivative of pH with respect to H total, right, and that was equal to minus d H total by the pH. Or let me just use this variable, I guess. So let's say let's say what is the change in pH or delta pH change you are fine with the change in H total, let's say. This you can know, right? Are you fine with the change in pH? If you are trying to buffer a system at pH 7 and you want, or you are only fine with 6.9 to 7.1, let's say, plus or minus 0.1, you will have a particular buffer intensity. And let's say if you are okay with 6 to 8, right, when your pH you want the pH that you are estimating or want to buffer the system at is 7, right, then you will have a lesser buffer intensity. So that is what you see here, and you need to obviously estimate H total, as in you will need to estimate the amount of acid or base that you think will be added to the system. So once you can understand how much pH change you are okay with, and you know how much acid or base will be formed in the system during the experiment or in the natural system, then you can obviously come up with calculating the buffer intensity approximately, right. So you have the buffer intensity now. So you know how much, not how much, you have the buffer intensity, and what is that equal to? You know that that is equal to 2.303 into concentration of H plus OH minus plus, let us say for a monoprotic acid, what is it now, B total into alpha naught into alpha 1, right. So for a specific pH, let us say you have H plus and OH minus to be, you can calculate that, right, they are fixed. So you need to be now able to calculate how much B total you need, right. So for that obviously you need to choose which acid. So how are you going to choose that? You will going to choose such that your pH will be equal to the pKa of your system, and which in this case you want it to be 7. So you can look up the relevant acids and bases that are available, and then you can see which particular pKa will be relevant to pH 7, right, in which case will you have pKa equal to pH 7. So you might not have something that's or you might not find a system that would play a passive role in your experiment and also be equal to or nearer the pH of 7. So you will need to go with some you need to have some leeway here. So the carbonic system or carbonic acid, you know that it has a pKa1 of 6.3 and you are trying to buffer at pH 7. So okay, you can live with that, you can choose that. Or the phosphoric acid, it has 3 pKa values. What are they at? I think around 2.3, 6.7 or 7 and 10.3. So that is something you can choose, the phosphoric acid, right. So again, so what do you need? Once you calculate the buffer intensity, you need to choose which buffer or which compound to choose. So how are you going to go with that? You are going to choose a compound whose pKa is near the pH you are trying to buffer at, right. So once you get that, you obviously have which acid base to choose, right, and how much, you can then calculate B total from the buffer intensity or this equation, and you are done with the two variables, right. So that is the design again. So first you need to look at how much pH change are you fine with or can you live with, and then you are going to calculate obviously what now, the buffer intensity, and then from that you will choose the relevant buffer, or which particular acid base system do you want to choose. So for example of pH 7 we said carbonic acid, or what is it now, the phosphoric acid, with the pKs around 6.3 and 6.7 respectively, right. And then once you have that, you can plug that in and get the total base or total acid that you need to add, right. So with that we are going to move on. So we are now going to discuss alkalinity, right, and that's something that's ever present, present in all the natural systems. So that's of considerable importance to environmental engineers, right. But before we go further, let's look at why we need to look at alkalinity, I guess, right. So in one of the previous examples or sessions that we looked at, I believe we considered an open system where we had carbon dioxide in the gaseous phase, and which is going to be in equilibrium with your aqueous phase, right. So and then we knew that, or we now know that, carbon dioxide, if it what do we say, changes phase from the gaseous to the aqueous phase, it can form H2CO3 in your aqueous phase, right. And then we are going to end up with an acid in your particular system, and then the relevant dissociations into either HCO3 minus or CO3 minus, yes. But in effect, let's say we are going to have an acid, what do we say, added to our particular aqueous system. So in general, let's say we know that the pH can go down, right. So let's say how would you arrest this particular decrease in pH in your natural systems, right. So in that case, alkalinity comes into play, makes sense. So again, alkalinity would help or assist in looking at neutralizing the acid. So it's also called acid neutralizing capacity. So let's look at what we are up to here. So we are now going to discuss alkalinity. So and that we can also understand that by the acid neutralizing capacity. Yes. And again, the important aspect is, it's ever present, right, because you have carbon dioxide and sources of CaCO3 and in your seabeds, right. You are always going to have considerable alkalinity in your particular system, natural systems, pardon me. And so thus that's something, or the variable that you always need to consider, obviously depending on the relevant organic or inorganic reactions or the interactions with these particular components here, right. So again, this is ever present, and that's the reason we are going to look at it. And one particular aspect that it helps with in our natural systems is that it resists the change in, not change, pardon me, decrease in pH. A buffer would resist a change in pH in either directions, as in either decrease or increase with addition of the acid or base, right. But here we are talking about resisting decrease in pH whenever there is an addition of your acid, right. So here we are going to move on to that. So here we are going to look at two aspects. One is the theoretical definition, and one would be the practical definition, which are practical measurement, which we look at in the lab. And so alkalinity, it's defined as the concentration of OH minus minus concentration of H plus plus concentration of HCO3 minus plus 2 times the concentration of CO3 minus. So obviously this would be the case when the units are in molar units, but if they are in equivalents per liter or equivalents, let's say the units, what are they going to be? OH minus minus H plus plus HCO3 minus plus CO3 minus, right. So again, the difference here is that in this case we are using the molar units, and here we are using the equivalent units, right, the equivalents here. So alkalinity can be expressed in terms of either as CaCO3 or equivalents per liter. Usually these are the two what we say units looked at with respect to alkalinity now. So again, now let's try to understand what it is that we are looking at here. Let's look at each of these components. In general, we are going to look at this particular equation now, right. So it's acid neutralizing capacity, right. So more or less you are trying to look at or quantify all the bases that are going to be present in your system. So OH minus, HCO3 minus and CO3 minus, but because CO3 minus can take or neutralize 2 protons, that's why we have the 2 term here. And obviously if we look at the equivalents, we do not need to have that here, because that will be taken care of when you calculate the relevant equivalent concentration here. Again, so we need to look at all the bases present in the system. They are OH minus, HCO3 minus and CO3 minus twice 2, because it can neutralize 2 protons, right.
and obviously you need to subtract the proton here, and this obviously would be valid again when what now the carbonate system is the only predominant acid base system in your particular solution, right. So, again the theoretical definition considers that only the carbonate system is the predominating acid base system in your particular solution here, and based on that alkalinity, which is nothing else but acid neutralizing capacity, right. So, if you are putting in an acid, right, or titrating your solution with an acid, let us say, right, what are the compounds that can neutralize your particular acid, and so we list the relevant bases here, which is OH minus, right, always present in solution, and then HCO3 minus and CO3 2 minus with the relevant coefficient, and obviously subtract H minus, right. And again this is a working definition that most people understand, but let us look at the fundamentals or basis for this particular aspect, right. So, in general if you look at this particular case, and thus I believe you can look at Stum and Morgan for this particular case. So, in general when we do the component balance, right, if you remember we always looked at them with respect to H plus and the most deprotonated form CO3 2 minus, right. But in this case, let us say if we consider the reference to be H2CO3, right. So, the alkalinity titration is going to be with respect to the reference of H2CO3 now. So, in that case instead of having CO3 2 minus, if we consider our components to be H plus and H2CO3, right, what would H total be? Let us try to write that down, and what are our species here? So, another new components that I am considering are H plus and H2CO3, and what are the species? OH minus, H plus, and what else? H2CO3, HCO3 minus, and CO3 2 minus, and this obviously is in the closed system, right. So, H total is going to be equal to what now? H plus obviously, right, and what else? Minus OH minus, yes, and now because we have a component as H2CO3 and not CO3 2 minus. So, you are going to have two what do we say terms here, two additional terms here, and what are they? HCO3 minus minus 2 times of CO3 2 minus, right. Again if people are unable to understand this, let me plug this up here or plug this down here. We have H, and what do we have here? H2CO3, this is nothing but the tableau, right, and these are the various species OH minus, H plus, and H2CO3, let me write that down, I guess, HCO3 minus and CO3 2 minus. So, how many H plus do I need to form one OH minus? Minus 1, and this is going to be 0, and how many H plus do I need to form one H plus? 1, and thus here is going to be I need 0 H2CO3 to form H plus, and again here it is going to be 0 and 1. So, obviously HCO3 minus is H2CO3 minus H plus. So, that is why we have it here, and how can I form CO3 2 minus? By H2CO3 minus 2 times of H plus, and from this we can look at the total component balance, which is H plus minus OH minus minus HCO3 minus minus 2 CO3 2 minus, and this is nothing but as you see minus the alkalinity here, right. So, in effect the total H was going to be the negative of the alkalinity, the theoretical definition of alkalinity, especially when you consider your reference or the component to be your H2CO3. So, again the reason we are looking at it will be apparent later, but please keep this in mind that here the reference is with respect to the component H2CO3, right. Again the theoretical definition is valid when only the carbonate system is the predominating system. So, let us go back to the practical definition here, right, and how do you go about measuring your particular alkalinity, right, in the lab. So, in general I guess you have a what do we say solution here, right, and then you are going to titrate it with a strong acid, yes, and then you end up measuring a particular color change or an endpoint. So, the key here is you have an endpoint, right, you end up measuring the amount of acid that has been consumed to reach that particular endpoint, which is either measured by you can use your pH meter, or depending on the indicator that you want to look at, right, which would give a color change at that particular pH endpoint, yes. So, this is how we are going about it. So, here in general let us say when would the practical definition of your alkalinity or practical measurement of alkalinity be the same as what you would calculate from your theoretical definition. Again when is that? only when the carbonate system is the predominating system, right? Yes. So, again the endpoint we typically look at, that's something that we can calculate. So, I believe we looked at this in our buffer intensity and such when we were trying to calculate the equivalence point. So, what was that? I think pH of the equivalence point was 0.5 times pKa minus log CO3 total, right? And this is something that we end up with or ended up deriving when we considered system where we had a strong acid HA and a weak acid NAB, right? And CO3 total is for NAB, yes. And this is something that we calculated there. I mean, we calculated something like pH equal to equivalence point equal 0.5 times pKa minus log B total, right? But obviously in this case your B is CO3, and that is why we end up with this equation. But you might be you know, those people who are paying I guess closer attention, right, might be able to point out that in this particular derivation here we looked at, let us say, only a monoprotic weak acid, right. But here your carbonate system here H2CO3 is a diprotic acid. So, you know, let us see, you know, but it turns out that, you know, looking at the relevant underlying aspects, that the relevant equation is still valid, but let us see how we can go about that. So, again what is the experimental definition here? Alkalinity would be equal to the amount of acid required to reduce pH of solution to, and what was our reference earlier, if you remember that, that was the H2CO3 equivalence point. This is the practical definition anyway, right, and we looked at the theoretical definition earlier, yes. And so, now how do we go about this, right? How do we you know, end up calculating the equivalence point here? So, we did look at one particular case, but again as I just mentioned, you know, it is for a monoprotic what do we say, weak acid, right, titrated against a strong acid, and we end up calculating the equivalence point there, right. So, here let us see how we can go about it here. So, keep in mind that here we are measuring the acid neutralizing capacity, right. So, we are adding enough acid to be able to neutralize this particular or take care of this particular acid neutralizing capacity. So, at that equivalence point the key is that the alkalinity is going to be 0. Why is that? Because you added enough acid to be able to neutralize that A and C or the alkalinity. So, right. So, what is that particular equation, or where does that leave us? So, the alkalinity, which is equal to what now? Concentration of OH minus H plus HCO3 minus plus 2 times of CO3 2 minus, right, and this is what we have. And let me try to simplify this further. So, that is going to be OH minus H plus alpha 1 plus 2 alpha 2 into CO3 total. Again, to refresh your memory, what do we have? What are these alpha 1 and alpha 2? They are the ionization fractions. So, alpha naught will give you an idea about H2CO3 by CO3 total, whereas alpha 1 and alpha 2 would give you an idea about the other species, which are the deprotonated forms here, HCO3 minus by CO3 total and CO3 2 minus by CO3 total. So, looking at this particular or using these particular variables that we are aware of earlier, you know, we end up with this particular equation. But we know that at equivalence point, what do we know? The alkalinity is equal to 0. So, let us plug this in here please. So, the alkalinity is equal to 0 is equal to what now? OH minus H plus alpha 1, right, yes, plus alpha 1 plus 2 alpha 2 times CO3 total. So, and we know that, you know, from our carbonate system, what is that, let us say, and this is the pH here, this is the speciation diagram we are looking at, right. So, H2CO3, this is the profile, HCO3 minus, this is the profile, and for CO3 2 minus, this is the profile. I believe I have a figure here, right. Yeah, this is what we also looked at with respect to our buffer intensities and such, right. So, this is H2CO3 here, HCO3 minus here, and CO3 2 minus, right. So, at which particular point do you end up more or less, let us look at this, try to approximate the scenario, end up neutralizing all the bases present, and that too with respect to H2CO3. So, the bases are CO3 2 minus and HCO3 minus. So, if it is this particular point, no, you haven't yet neutralized anything here, and even at this particular point, or no point as in at this particular pH of 8, we still have HCO3 minus. If see we further need to titrate all the way till here around 4.5, right, where you would end up let us say neutralizing all the bases which are CO3 2 minus and HCO3 minus in your particular system. Keep in mind that the reference is H2CO3 here, right. So, it is approximately around 4.5, and that is what actually standard methods uses. So, we are going to come back to that, and here we have CO3 2 minus, right. So, again what I was trying to point out was that at that particular pH, which was around 4.5, let us go back to the figure, that is a better case, right. You see that the CO3 2 minus is negligible, HCO3 minus will be at very low quantities, but CO3 2 minus is certainly remarkably negligible, right. So, that is keep that in account. So, also at 4.5 pH, right, the OH minus concentration is also negligible. So, neglecting OH minus concentration, and what else now, the CO3 2 minus concentration, right. We are going to try to simplify this further. So, is equal to alpha 1 times CO3 total minus concentration of H plus, right. And what is alpha 1 here? Alpha 1 we know is going to be in this case, let me try to write down alpha naught in the first case. The denominator will be equal to H plus square plus what now? H plus into K1 plus K1 K2, the equilibrium constants. So, now if I write down the denominator, I can now be sure of being able to write down alpha 1, that is going to be equal to H plus into K1, right. If it is alpha naught, it would have been H plus square by this denominator, alpha 1 would be this particular term H plus into K1 by the denominator, and alpha 2 would be K1 K2 by this particular term in the denominator, right. Again, so at this particular case, let us see how we can simplify this further. So, alpha 1, let us see, I am trying to simplify that further, and that I can write as K1 by H plus K1, and why is that? Because K1 K2 will be, let us say, negligible when H plus concentration is higher, and once I simplify that, I can cancel out H plus. So, K1 K2 will be negligible when H plus concentration is high, which is the case because pH is equal to or around 4.5, right. So, I am neglecting K1 and K2 in this particular term in the denominator. So, then I can cancel out the H plus, and then I end up with K1 by H plus plus K1, and so 0 is equal to, or let us say H plus is equal to what now? Alpha 1 is K1 by H plus plus K1 into CO3 total, right. And so, if I end up solving for that, H plus will be equal to CO3 total into K1 to the power of 0.5, and now we get the relevant similar form, right. So, now pH of the equivalence point is nothing but, right, 0.5 into pKa minus, or pKa or pK1 in this case, right, minus log CO3 total. And as you see, this was similar to our particular case when we looked at just HA and NAB. And why is that? Because at pH of 4.5, right, we are neglecting CO3 2 minus. So, in effect, the system we are considering that to be a monoprotic system here. So, anyhow, we end up with this particular equation. So, let us plug in a particular set of values. So, I think an example that I have here is that CO3 total, if I take that to be 3 into 10 power minus 3 molar, right, and what is the pH or the equivalence point pH, I guess that is 0.5 times pKa1 we know is 6.3 and pKa2 is around 10.3. So, that is what we are going to use here, 6.3 minus log of 3 into 10 power minus 3. So, the value I have here is 2.52, right. So, now I end up with something around 4.4, right. I end up with around 4.4, and thus as you see is remarkably or similar or nearer to the method or the pH, pardon me, that is going to be followed by the standard methods, right. So, the standard methods would define your particular alkalinity as titrating with acid until you reach the equivalence point of H2CO3, and to account for loss of CO2 into the system, into the gaseous phase during your titrations and such, standard methods would more or less specify, or not more or less, pardon me, would specify an endpoint of 4.5, right. So, again we just looked at the relevant derivation with respect to alkalinity. So, let us look at what that means. Let us say initially now my particular system is around pH 10, let us say, right. So, I can calculate given the CO3 total, right, I can calculate what alkalinity is going to be equal to, right, and we know that from the particular cases of our definition of alkalinity, OH minus H plus HCO3 minus plus 2 times of CO3 2 minus if any present here, right. This is the theoretical definition. So, again practically what happens now, let us say I am starting at pH 10 and I want to end up at 4.5. So, that means I need to obviously add an acid or titrate with an acid. So, I am starting from 10 and I keep adding acid. So, what is going to be consumed here, H plus is going to be consumed by HCO3 minus, right. Any H plus that you add is going to be initially neutralized by HCO3 minus and be transformed into H2CO3, and keep in mind that H2CO3 was our reference, right. So, I keep going down and as you see the HCO3 minus, the concentration that keeps changing and decreasing and so on until almost all of it, but not all of it though, is going to be in the form of H2CO3, and that is what you would understand in your particular system too, right. So, these are the concentrations at pH particular 10. You can calculate the relevant concentrations and you can plug them in, or obviously you can also titrate that and then calculate that, but because you know how to use Vmintek or such, you can calculate the equilibrium concentrations of HCO3 minus and CO3 2 minus from Vmintek and just plug them in, or you can go back to the lab and titrate and look at the amount of acid required to be able to neutralize the particular solution, or neutralize, pardon me, reduce the pH of the particular solution to the H2CO3 equivalence point, which is 4.5, right. So, with that I will end today's session, and then in tomorrow's session, or pardon me, the next lecture session, we are going to look at, let us say, when would your particular practical definition of alkalinity not be similar, or not be in consonance with your theoretical definition of alkalinity, and depending on time we are also going to start talking about acidity, which is nothing but, let us say, base neutralizing capacity, I guess, right. And with that I will end today's session, and thank you.